All right. Well, thank you very much. It's my pleasure to speak in the workshop. So thank you very much for organizing. And yeah, I would have preferred to be in Bonn, of course. Anyway, so also thank you, audience, for being in my talk, at least virtually. Right. So I'm going to be talking about hyperbolic Poisson-Voronoi tessellations. Yeah. So first, let me just briefly remind you what a normal Poisson-Voronoi tessellation is. I know it's been discussed also in previous talks, but yeah, who knows, maybe somebody might show up that didn't go to those talks. So anyway, we take a Poisson point process of constant intensity on, in this case, the plane, which just to, if you don't know already, so that can be described as just a random set of points with the property that for every set, the number of points that falls in the set follows a Poisson distribution with mean lambda times the area of the set. And if I have two disjoint sets, then the point counts are independent. And then we define the Voronoi cell for each of these random points. So the Voronoi cell is just everything in the plane that is closest to that point out of all the other random points. And then finally, so for each of these cells, we're going to flip a coin with probability P, we're going to color it black, and with probability 1 minus P white, independently for all the cells. So here's what that might look like. And but of course, so whenever I say black in the picture, is going to be light blue, just because I thought that looks better. So here's a computer simulation what this process might look like. And so what we're interested in is percolation, which I guess for us probabilists is just defined as the existence of an infinite connected cluster of black cells or light blue cells, right? So in particular, of course, only a finite picture, but so the question is, does there exist, can I walk infinitely far staying only in the blue, right? So if I was some kind of snail, would I be able to travel infinitely far, never touching the white? And so the critical probability for percolation is a value of the parameter P, such that if P is less than that value, then the probability of percolation is 0, right? So with probability 1, all the black components will be finite. And if P is bigger than PC, then there has to be a positive probability of finding such a component. And so you can see it follows from standard properties of Poisson point processes that this actually does not depend on lambda. But yeah, given the time frame, I guess most people will probably already know. All right, and so here's, I guess, one of the main results for this model, or the main result, which tells us what the value of PC is for the case of the Euclidean plane. So that was done. So first, Zvavich proved in the 90s that there is no percolation when P is less than or equal to 1/2, right? So that shows that PC is bigger than or equal to 1/2, right? So when P is less than or equal to 1/2, then with probability 1, all the components will be finite. And then later there was a very clever involved argument by Bolobach and Riordan that showed that when P is strictly bigger than 1/2, then indeed there's a positive probability of finding some infinite black component. And in fact, by fairly standard in percolation theory arguments, you can see that if P is bigger than 1/2, in fact, there will be precisely one infinite component with probability 1. So all the if 2 points are in infinite black clusters, then there's also a black path between those 2 points or those 2 cells. And yeah, so in a sense, that was only the beginning. So what since then there's been a fair amount of work still on this model, especially aimed at understanding what happens to the model exactly when P is equal to 1/2. But yeah, but today we're going to be discussing something different, right? So we're going to be interested in defining this model on the hyperbolic plane. And so yeah, so again, so please don't be offended. So I'm just I'll give a short introduction to what the hyperbolic plane is. I guess so. If before I started working on this topic, I would probably have benefited from such a explanation. But yeah, I know that. So Daniel already gave very nice lectures earlier in the trimester on hyperbolic stochastic geometry. But I guess yeah, not everybody might have followed that and be familiar. But anyway, so what's the hyperbolic plane? So it's a surface with the property that every point, so two-dimensional surface with the property that every point locally looks like a saddle point. And yeah, so more specifically, it has constant Gaussian curvature -1, but it's not really important what that means. So, yeah, in principle, it just describes exactly how these saddle points look. And that is not necessarily very easy to visualize what such a surface that is a saddle point everywhere might look like. But yeah, here's a picture of what it might look like. So this picture I actually screen grabbed from an article in the Mathematical Intelligencer from the 1990s. And so since I'm interested in drawing Voronoi diagrams in the hyperbolic plane, I actually emailed the author to ask how he made the picture. But then he told me that he'd actually drawn it by hand, and the mathematical intelligencer people hired an airbrush artist to make the picture look nice. So I guess in the 90s, journals still did something for improving our articles. But anyway, then he also said, yeah, but don't you know it can't be done, right? So he was referring to this result by Hilbert that says that, so if you want to faithfully represent the hyperbolic plane in 3 dimensions, then you cannot do that, right? In the sense that, so if I imagine that it lives in some very high dimensional space and I want to make a surface in 3 dimensions that behaves the same, in the sense that I can make a bijection between the 2 surfaces, such that if I take 2 points in the one surface and the image under the bijection and the other surface, then the distance of the shortest curve that stays inside the surface, the length of the shortest curve that stays inside the surface, is the same for both surfaces. So you can't do that if you want the bijection to be 4 times continuously differentiable. But actually, it turns out that so apparently it can be done. There's a later work by Kuiper that says that it can be done even in a 1 times continuously differentiable way. But unfortunately, this paper doesn't give much hints on how you could actually draw such a surface in Maple. And I've actually tried to enlist the help of several geometers in the past years without any success so far. But yeah, but there are ways to conveniently depict the hyperbolic plane using coordinate maps, I guess you would call them. So there's several ones. The half-plane model, Klein-disk model, and the Poincare-disk model are a few of them. This image is actually, well, this is called the Circle Limit 3. It's artwork by the Dutch artist Escher. So we have a lot of Dutch artists today. So the idea is that, right, we have this hyperbolic plane, a surface in some higher dimension. And so there's a coordinate map, meaning there's a bijection between the open unit disk and the surface. But we equip this open unit disk with a different metric. So the idea is that if I take 2 points here, the metric tells me a certain distance, and that's exactly the length of the corresponding 2 points, the length of the shortest curve that stays inside the surface between the 2 corresponding points. And yeah, so the idea behind this picture is that all these fishes in the picture, they look different, of course, but actually in the real hyperbolic plane, let's say, they would all have exactly the same shape. They would look exactly the same. And yeah, as you can see, they get smaller and smaller as you approach the boundary, which is because actually that's infinitely far in the metric. Right. So in a bit more detail, these things, they're not going to be important for the rest of the talk. But yeah, so what we have is it's the open unit disk, and there's a metric which can be written down explicitly in this form. And also there's a notion of area, which just means, so if I take a subset of the unit disk, then its area is just, you just integrate that expression over it. So the Poincare disk has a lot of really elegant, nice properties. So one of them is, so if I take 2 points A and B, then that formula from the last slide tells me what the distance is. But if I just want to draw the shortest curve between them, then I can also just draw a circle that hits the boundary of the unit disk at right angles. And then it's exactly this circle segment is the shortest curve between the 2 points. And also so I can also speak of a hyperbolic disk, right? So just I take a point X and then take all the points Y that have hyperbolic distance at most R to it. And that will actually look also like a Euclidean disk, but of course, except that the center X will not be what the parent center is. So it will be a bit further towards the boundary. And of course, the radius won't be the Euclidean radius, but it still looks like a disk. And then, yeah, finally, just to mention, so there's, for every 2 points, I can find an isometry, so a map that preserves the distance such that A gets mapped to the origin and B gets mapped, for instance, to the positive x-axis. And all these isometries also preserve angles, for instance, between these geodesics from the previous slide. All right, so that's it for short introduction to the hyperbolic plane. So we can actually define the model Voronoi, Poisson-Voronoi percolation model in exactly the same way as we did for the Euclidean plane. So you just take a Poisson process of constant intensity, which now means that it's a random set of points with the property that if I take a set A, a subset of the hyperbolic plane, then the number of points that falls inside it is Poisson distributed, which mean lambda times the area, but the hyperbolic area of A. And again, for disjoint sets, the point counts are independent. And we can define Voronoi cells in the same way, right? But now we use the Voronoi distance. Sorry, Voronoi distance, the hyperbolic distance, excuse me. And again, we just flip coins to decide which cells are going to be black and which are going to be white. So here's a computer simulation of what that might look like. This is with p equals 1/2, and I think lambda is equal to 1. And as you can see, so there's actually, in principle, supposed to be infinitely many points visible. Of course, not really. And yes, these cells are actually polygons, right? So they're hyperbolic polygons. So these, the sides are actually circle segments, a part of a circle that will somehow hit the boundary of the disk at right angles. Right, and so again, we say, yeah, percolation is again the same thing, right? So we want to find an infinite connected cluster of black or light blue cells, right? We're here in principle, so we want one that's infinitely large, meaning that, so we want to be able to travel along the blue towards the outside of the circle, right, to the boundary of the circle. That's one way to see it. And we can again define the critical probability in the same way. But now there's no reason to assume that it won't depend on lambda, on the intensity parameter. And yeah, so about 20 years ago, there was a really nice paper by Benjamini and Audetrom on this model, where they proved they proved some nice results, and they also had some very nice methods that continue to, made a big impact in percolation theory, I think. So one of the things they proved is that for every value of lambda, this critical probability is strictly between 0 and 1/2. And in fact, it does depend on lambda, because if you send lambda to 0, then the critical probability will also go to 0, right? So it's certainly not, right, yeah, so it certainly depends on lambda in some way. And what also was quite striking actually is that, so also qualitatively, they show that it behaves quite differently from the Euclidean case. So this first thing is of course the same, right? So more or less by definition of the critical probability, if P is below PC, then all the black clusters are going to be finite, right? And they showed that then if you're above 1 minus PC, then there will be infinite black clusters, but there will be only one. So any 2 points that are in an infinite black cluster are also connected by a black path. But now, since PC is strictly less than half, there is actually a gap between these two things. There's this middle regime where, in fact, there will be infinitely many different black connected components. So there are lots of different groups of points that are infinitely large connected clusters, but they don't connect to each other. And he says, so that doesn't happen in any Euclidean model in any dimension in the literature, as far as I know. And so here's a diagram that they had in their paper that sort of illustrates the results and also some of the questions that they posed. Right, so here's PC, right? There's 1 minus PC. They also prove that it's a continuous function of lambda. And so below PC, there will be no infinite clusters. Above 1 is PC, there will be only one infinite cluster. And then between them, there will be infinitely many clusters. And here it approaches 0. So one thing this picture, for instance, suggests, right, is that PC will tend to 1/2 as lambda goes to infinity. And that, you might also have guessed that based, of course, on what we now know about the Euclidean model, maybe. So in particular, they phrase this as a conjecture in their paper. So they conjecture that as lambda goes to infinity, PC of lambda will tend to 1/2. And that's something that, together with my doctoral student Ben, we recently proved. And then another thing that we were able to answer the following question by Benjamin and Schramm. So they asked, so we know PC lambda tends to 0 as lambda goes to 0, but at what rate does it go? And so what we're able to show is that it behaves like pi over 3 times lambda. Basically like pi over 3 times lambda, which is actually a little bit below an upper bound that Benjamini and Schramm gave in their paper. All right, so let's, I'll first discuss the first result. So as you might have guessed or imagined, so what we do is we can leverage a lot of the work that has been done for the Euclidean case. And the intuition behind that is basically the following. So if you look at the hyperbolic plane at a very small scale, so if you zoom in around a point, then, if you look at these expressions that I had on the previous slide, you see that actually the metric basically starts to behave like a constant multiple of the Euclidean metric. If I take a small enough disk somewhere in the hyperbolic plane. And also similarly for the area function. So areas inside a small, if I take a small enough disk, then the area of any subset that is contained in there, they're all behaving like a certain constant depending on where we are times the, let's say, Euclidean area. So the geometry is more and more Euclidean as the scale gets smaller and smaller, which is not really specific to the hyperbolic plane, of course. And at the same time, if we increase the point intensity, then the points get packed closer and closer together. So it makes sense that as you put more and more points there, as you drop more and more points on the hyperbolic plane, you increase intensity. Typically, all the cells get smaller and smaller, and they start to look more and more like an ordinary Euclidean Poisson-Voronoi tessellation. Now, of course, that is not really enough to prove the result because percolation is a global property, and so there's much more to it. But I have 30 minutes today. I'm totally not complaining about that. But so I'd have to refer you to Ben. Ben did a very good job at actually explaining this proof over the course of a 1.5 hour lecture in the Percolation Today seminar last year, so you can find his talk there. And of course, we have the paper also on archive, and fairly soon it will appear in a journal, I hope. Anyway, so that's all I'm going to say about this particular result. because I want to spend a little bit more time about the other result. And that's also partly because this meeting is about high dimensional random geometry. And of course, my talk is really two-dimensional, for which I really apologize. But at least in this lambda going to zero regime, a lot of the intuitions and a lot of the proof techniques are kind of similar to what happens in high dimensional percolation. So what's the overall strategy? So what we're going to do is we're going to take this Poisson point process, but we're going to add one extra point. So we're just adding the origin for convenience. We add one more point. It won't make, and we color the origin black. So it's not going to make any difference about whether or not there exists an infinite black component, right? If you just add one black point. And so what we're going to do is we're going to take lambda is going to be very small, and we're for an upper bound on the critical probability, we take p equal to a little bit more than the value that we claim is roughly the critical probability, and we're going to explore the cluster of the Voronoi cell of the origin, right? So and we're going to show that it contains, you can define a subclass or a subgraph of it, let's say, that behaves like a supercritical Galton-Watson branching process. And then for a lower bound on PC, what I'm going to do is I'll take P now a little bit less than this value. And then, well, what we have to show is that there is no infinite black path starting from this cell of the origin. Right, so that's very briefly how the proof goes. Here's a bit more intuition, as it were, for the result. So what's relevant is something called the typical cell, which I guess several previous speakers have also mentioned. So the typical cell is basically the thing that I described already previously. So I'm going to add the origin, and then I'm going to take a Poisson process, I add the origin, then I look at the Poisson cell, the Voronoi cell of the origin. That's the typical cell. And so it's different. It's not the same as the Crofton cell or the zero cell, which Zakar mentioned in his lectures. Yeah, so I always find it a bit confusing because I'm adding the origin, but then the zero cell is not the same thing. Anyway, so what you can do is you can take the zero cell, and then you can say, okay, I'm interested in the number of sides that it has, the number of corners or the number of neighboring cells. And I'm going to look at the expectation. And quite surprisingly, maybe, there is an exact expression known for this expectation that was computed by Yukina Isokawa about 20 years ago. And so this also kind of, in a sense, confirms the intuition that I gave previously about the lambda to infinity proof. Because you can see that, so lambda goes to infinity, this term here disappears, and then we get 6, and you can work out that that's the expected number of corners of the typical cell in the Euclidean plane. And on the other hand, if lambda goes to 0, then you see that this becomes a dominant term. And so what we're basically saying is that if we take p equal to pi of 3 times lambda, then the expected number of black neighbors of the typical cell will be roughly 1, right? And if we take it a little bit bigger, then in expectation, you have more than 1 black neighbor. And so, yeah, so if I had a branching process with strictly more than 1 child at each time, there's a positive probability that survives. On the other hand, if I take p slightly less than this value, then the expected number of black neighbors is strictly less than 1, and then you would expect, so a branching process would then die out. All right, so here's something that, so I don't have time to do that, of course, but you can kind of vary on the computations that Isokawa did to determine this expectation, and then you can actually see that for almost most of the neighboring cells of the origin, the distance between the 2 points will actually be very close to this number. So 2 times the log of 1 over lambda, which of course goes to infinity. You know, it grows with lambda, or grows as lambda goes to 0. So yeah, And so what we do when we construct this tree, so we're going to try and follow a breadth first search procedure. We start from the origin, then we try to find black neighbors of the origin, and after that we try to find black neighbors of each of those neighbors, right, which will be their children. But when we find the neighbors or the children of a particular point, we're only going to look inside an annulus of constant width, right? So it has, we know that most points that are neighbors, that have a cell that neighbors the typical cell, will be at roughly this distance. So we only look inside there. And also we're going to select these children in such a way that the angle between two consecutive children, right, they're all, well, if I place the point that I'm exploring at the center of the Poincare disk, there will be angles between all these points. And I'll make sure that the angles aren't too small. So they can be fairly small, but there's some small constant. And I'm going to select only children that whose pairwise angles are big enough. And so what we claim is that if you do this, then you can make sure that in every step of this exploration procedure, right, as I'm doing building this tree, imagine that at some point I've already found a whole bunch of points, right, that I've added to my tree. And I'm looking for a new point, but of course I already have collected all this information about regions of the hyperbolic plane that I've seen before. And so what we claim is that if you do this, then in fact what you've seen before is not going to bother you too much, right? And yeah, I can only share some intuition with you here. So imagine that here is a parent, and I'm trying to explore its children, right? So this is a child that I'm about to explore. And imagine that I know that, so all the tree that I've seen until now lives in the white area around here. And I claim that, and imagine that this purple area, I haven't really been exploring there, right? I haven't collected any information about it. So now I claim that actually, as I start exploring from the red point, I'm going to stay inside this purple area, right? And so if you look at the picture on the left, that maybe seems rather unlikely or unbelievable. But so remember also, so this distance is quite long, right? It's 2 times the log of 1 over lambda. Now, if I now apply an isometry such that this child is the center of the Poincare disk, then because of the information, well, the facts that I mentioned about the geometry of the Poincare disk previously, what it's actually going to look like is this, right? So now, so this is the parent, this opening, this sector here. So here there are 2 rays, which are geodesics with an opening angle theta. And in fact, what they turn into disks which go through this point, have the same opening angle here, and hit the boundary at the right angles. Yeah, so in any case, you see that now most of the unexplored area is almost all of the Poincare disks. So there's a way to make this work so that we actually do get independent increments, independent Austrian distribution. And you can kind of reuse these computations for the typical point to show that the expected number of children in each exploration step is strictly bigger than 1. And then, well, let me briefly mention the lower bound, right? So now what we do is we want to show there are no infinite black paths starting at the cell of the origin. So naive approach might be to say, so what I'm going to do, I'm going to try and compute or bound the expected number of paths of length k, and then let k to infinity go to infinity, and hope that the expectation goes to 0. But unfortunately, that is technically very hard to realize, because so for this upper bound construction, I was allowed to have, I can select only those adjacencies that I like, which have roughly the right distance and whatever. But when I want to bound all possible paths, let's say, then in principle, there might be paths that make a lot of use of unusual parts of the tessellation. So it's technically not so easy. But to get around it, what we do is we count something slightly different. Essentially, we kind of break up infinite paths into smaller paths which are behave reasonably. Yeah, I realize that's not much of a proof sketch, but anyway, that's roughly some ideas about how the proof goes. And then, yeah, just to conclude, so here are some things that might be interesting for further research. So one thing that seems, well, would be really great, I don't know how likely this is going to work, is you could, so the question is, would it be possible to use our proof or some variation of our proof for lambda going to infinity to study the critical case of the Euclidean plane? All right, so in particular, yeah, so if you don't know what conformal invariance of Poisson probabilities means, then yeah, I guess I don't have time to explain it to you, but yeah, that would be quite nice if there some information about the Euclidean critical case could be obtained from this. And then, yeah, some other obvious questions are, is PC of lambda strictly increasing, or if it's differentiable? And then finally, one other opportunity for further work of a slightly different kind. So Ben, my co-author, will soon submit his PhD thesis, and so maybe you have an opportunity, if you have a postdoc position available, it might be a nice opportunity to for you doing further work with him. All right, that's it. Thank you for your attention.